This is section 1.4, the properties of matter. So this section here is it's a pretty brief section, and we're going to cover a few terms that are used in chemistry. So let's begin by thinking about different types of properties. Sometimes properties are what we call quantitative, which means that we make some sort of measurement. So for example, a density of a material, like the density of water, would have a number associated with it, and then also units, for example, grams per milliliter. Or the mass of something might have some number. Something is 50, and then it would have units, and that would have the units of grams, for example. And then there's qualitative observations or qualitative properties. Now, these ones don't require necessarily a quantitative measurement. So, for example, I might say something is red. That's an observation that we're making about something, and it's a property. The color of something is red. Or something is hard or soft, but we don't have a number associated with that particular measure or that particular observation. So some properties are quantitative, other ones are qualitative. There are what we call physical properties. So example of physical properties are ones that are not directly associated with chemical change. And so examples of that include the color of something. If something is red, that's a physical property. The temperature that something melts at. So for example, water at atmospheric pressure melts at 0 degrees Celsius or 32 degrees Fahrenheit. The boiling point. That's the temperature at which something undergoes a conversion from a liquid to a gas under atmospheric pressure. The boiling point of water is 100 degrees Celsius or 212 degrees Fahrenheit. Those are physical properties. So a physical property is something that can be identified, it can be observed or measured without changing what the substance is. So for example, if we take water in the liquid state and boil it into a vapor, steam, it's a different material, right? It seems very different. It's a gas, it's a very highly energetic gas, steam, very dangerous. On the other hand, if we cool it back down, it becomes liquid water again. So it's still water. In both states, both as a liquid and as a vapor, as a gas, that water or steam is still water. It's still H2O is the chemical formula we use it. So that's a physical property. The state of the matter or the boiling point. Then there are what we call chemical properties. So a chemical property is something that we would observe that involves chemical change. For example, hydrogen gas reacts with oxygen gas to form water. So if we run that reaction in some sort of container, take hydrogen gas and oxygen gas to form water, there's a chemical change occurring. We can kind of tell that's chemical because if we took that water, we would observe that it's very difficult to convert it back into hydrogen and oxygen gases. It pretty much is stuck as water. So that's an indication that it was some sort of chemical change. We'll get more into details about what that is, more specific about what a chemical change, but in a sense it has to do with this idea of irreversibility, meaning you can't go back the other direction. Another example given here is baking cookies, right? So if you bake a cookie, you take the flour, the sugar, the eggs, all the materials that you put in there and bake it, you got a cookie. But if you take that cookie and you leave it out on the counter, it doesn't turn back into sugar and flour and eggs and oil and all the other things that you put in it. So there's a certain irreversibility about it. It turns out baking is essentially a chemical reaction or a group of chemical reactions. We then have what are called extensive and intensive properties. We'll get into those a little bit later when we talk about some calculations of density. Extensive is a property that depends on the amount of material that you have. For example, if I were to say, hey, there's a 2-liter bottle of Coca-Cola or Pepsi, and I want to know how many calories are in it. The number of calories that are in the Coca-Cola or the Pepsi depends on how much of it you drink, right? If you drink only a capful of the drink, you can only get a few calories, maybe 5 or 10 calories. But if you drink the whole 2 liters, you might get 5, 6, 700 calories out of that. So that's an extensive property. The number of calories depends on how much of it you have. Intensive is the opposite. It actually doesn't depend on how much you have. Now that might seem a little counterintuitive. We would think most properties depend on how much you have. But it turns out there's certain things that it doesn't. So for example, suppose I have an apartment with 3 or 4 rooms in it, and I have all the doors open and all the windows are closed to the outside, and the temperature is pretty much the same throughout the apartment. Now, that's maybe not likely to occur. There's always, I know in my apartment, one bedroom is always colder than the other, but let's suppose that the temperature is all the same throughout the apartment. And then I start closing the doors. Well, the moment you close the door, that's not going to change the temperature, at least not immediately. So the temperature in one room would be equal to the temperature in another room. The temperature of the entire apartment is the same as the temperature in one room, even if it's a small room. So what we're claiming is that temperature doesn't really depend on how much of the room you have. If you take one part of the room, sample another part of the room, sample a large part of the room, the temperature should be pretty much the same throughout. So that's an example of an intensive property. It doesn't matter how much of the room we're studying or how much of the apartment we're studying, the temperature is the same all the way throughout. Another example is what's called density, and we'll talk more about the calculations involving density. Density is defined as the mass of a matter, of a material, divided by the space that it occupies, the volume. And so if you have a little bit of water, the density of that little bit of water is actually the same as the density as a large cup of water. And the reason is the small amount of water, just like let's say a capful, it has a small mass because there's not very much of it, but it also has a small volume. There's not very much of that. So the mass divided by the volume is the same whether you have a little bit of it or a lot. Okay, so intensive properties do not depend on the amount of matter. Examples of that would be density and temperature. There are other ones as well. Color, for example. So here's an example, a sample problem 1.4. And again, just to keep reminding you about this, I advise you try as many of the sample problems as you can. Try the practice problems, the attempt and the build, A and B, before you do the ALEX problems. The ALEX problems are often more involved and more rigorous than the sample problems. So it's easier or perhaps preferable to do the easier ones and then work your way up to the harder ones on ALEX. So sample problem 1.4. The diagram in figure A, right below, shows a compound made up of atoms of 2 elements represented by the green and red spheres in the liquid state. Which of the diagrams from B to D represent a physical change and which diagrams represent a chemical change? So take a look at A. What you'll see are there are little combinations of what we call diatomics, a green one with a red one. So those little pairs of atoms, red and green, red and green, red and green, red and green. Those are actually called molecules. Now, a chemical change, really, even though the language in the text above here, was not really describing this in detail, a chemical change involves a recombination, a reassortment of the atoms. So if you look at one substance and there's one red atom with one green, and then you look at another substance and it's not one atom of red with one atom of green, that means a chemical change occurred. Okay, so let's take a look. In A, you have red and green. In B, all the reds are together in pairs and all the greens are together in pairs. That's a chemical change. A chemical, that's actually from atomic level, that's one way to depict what a chemical reaction is or a chemical change. Essentially, they're rearranging, right? The red is attracted to the green, but in figure B, now the green is attracted to the green and the red is attracted to the red. That's a chemical change. Whenever you rearrange the atoms, what they're bonded to, what they're connected to, that's a chemical change. Now, in C, it's not obvious, but it turns out that's a chemical change as well, because what has happened is the reds are no longer combined with the greens in a one-to-one combination attached together. They're now broken up. We've broken them up into separate particles, so that would also be a chemical change. And then in D, it's all little pairs of red and greens, red and greens, red and greens. So even though they're spaced out more in D than they are spaced out in A, they're still combined in the same way, one red with one green. So that's a change. They've changed, but they haven't undergone a chemical change because they're still in the same combination of red, green, red, green, red, green. So if it's not a chemical change, it's taking up more space, we call that a physical change. Okay? So as it says here in the strategy, we review the discussion of physical and chemical changes. A chemical change does not change the identity of the substance, whereas a chemical change does change the identity of the substance. Identity for this example would be red-green. That's the identity. So if it's red-green at the end, it's not a chemical change. Now, in D, they're more spaced out, so something happened. They've essentially undergone a conversion from a liquid to a gas, so we would consider that a physical change. Okay? So you can try the same thing with practice problem A and practice problem B, and then you can do the same thing with the checkpoints 1.4.1 and 1.4.2, and that'll give you some practice really at looking at physical changes and chemical changes, and then review for yourself some of the terminology here: intensive, extensive, physical, chemical, and you'll be pretty much, or quantitative, qualitative, and then you'll be pretty much set. So again, a brief section, not a lot of material there, but an important one, kind of understanding at the atomic level, at the molecular level, what a chemical change is.